In today's video, we are going to begin the last section of the class, which is using the ideas of trigonometry to lay down some basic tools that are used very often in Calculus 3 and Calculus 4. Today we're going to talk about the polar coordinate system, and we will continue to talk about that tomorrow. And then we will begin to talk about vectors, which is absolutely one of my most favorite topics in all of mathematics. So by the end of today, we should be able to state the meaning of the polar coordinates, which are called r and theta. We should be able to graph a point that's given to us in polar coordinates, and we should be able to convert between polar coordinates and the more standard coordinate system, which is called Cartesian or rectangular. Now, a coordinate system is just a system for communicating a position in 2D space to somebody else. And the coordinate system that we tend to learn early in our careers, the one that contains x's and y's, is called the Cartesian coordinate system, also known as the rectangular coordinate system. It's called the Cartesian coordinate system because it's named after this French mathematician slash philosopher called René Descartes. He was the I think, therefore I am guy. Now, the Cartesian coordinate system is something that we're all familiar with by this point, but let's just briefly review the significance of the coordinates in the Cartesian coordinate system so that we can contrast them with the coordinates in the upcoming polar coordinate system. If we were given a location in the Cartesian coordinate system, then they would give us a point x, y, with x coming before y following the alphabet. Now the x would tell you how far to travel from the origin either to the left or to the right in order to reach the specified point. And the second coordinate, usually represented by y, represents how far to travel either up or down in order to reach the specified point. For example, if someone asked me to plot the point where xy was equal to -1, 4, then I would plot that point on the xy plane by going 1 unit to the left to reach x equals -1, and by going 4 units up to reach y equals 4, and the corresponding point would be right hereabouts. So, the Cartesian coordinate system is an agreed upon way to communicate locations on the xy plane to other people. Now, the polar coordinate system is especially convenient when we're trying to describe to someone a position that lives on a circle, or something that is approximately circle-shaped. In the polar coordinate system, we also specify an object's position using two numbers. But instead of using x and y to represent the object's horizontal and vertical positions, respectively, we use two letters r and theta. What do these two letters represent? R represents the point's distance from the origin. How far away is it from the center? Theta represents the angle of the point. In particular, it represents the angle corresponding to the direction that points from the origin to the point. So as a quick sketch to explain these two definitions, here I would have the xy plane. And I'm thinking of a location maybe located right here. The coordinate called r is what describes how far away that point is located from the origin. And the coordinate called theta is what is describing the angle that will allow you to turn from the positive x-axis toward the point. So this blue dot would be the location that corresponds to the polar coordinates r and theta. For example, suppose that I wanted to plot the polar point where r was equal to 4 and theta was equal to pi over 4 radians. Then I can bring out my xy axes, but instead of traveling either vertically or horizontally by a specified amount, I'm going to start by turning through the angle pi over 4 radians, which is 45 degrees. How far will I travel in this direction? That is determined by the value of r. R is equal to 2 units. So the location that I end up, the point corresponding to these coordinates, is the location indicated by this sketched in blue dot right here. This would be the point 2, pi over 4. For some additional practice, let's go ahead and plot the location corresponding to the coordinates r equals 5 and theta equals negative pi over 2. So in this case, I would begin by turning clockwise by 90 degrees, because my angle is theta equals negative 90. And then I would travel along that direction from the origin a total of 5 units. And the location that I end up would be right down here. This is the location where r and theta are equal to 5, negative pi over 2. Now notice that this location would be relatively easy to describe in terms of Cartesian coordinates as well. If I were to describe this same location using x and y instead of r and theta, I would say to get to this yellow dot from the origin, don't move any to the left or to the right. Instead, just use 5 units straight downward. Now this point was relatively easy to describe in terms of both polar and Cartesian coordinates. But there are some formulas that we can use to help us to describe locations in polar and Cartesian coordinates, even if it's not so easy to exactly see what the conversion would be just with our eyes. For example, the formulas will give us a way to determine the location in terms of x's and y's of the blue point from the previous example. So let's figure out what those formulas might be, and then let's state the formulas. First, we'll give some formulas to help us to take a point which is currently described in terms of r and theta, and to convert that to a location described in terms of x and y. To figure out that formula, let's go back to this drawing. We are r units away from the origin, and we've turned through an angle of theta in order to reach that location. Now, what would the vertical leg of this triangle be equal to? The vertical leg of this triangle, on the one hand, would be equal to the point's y coordinate. But at the same time, the SOHCAHTOA formulas tell me that the opposite side of a right triangle, like this one, is equal to the hypotenuse times the sine of the angle theta. Simultaneously and similarly, the x-coordinate is what describes the horizontal leg of this triangle, and based on the SOHCAHTOA formulas, this adjacent side would be equal to the hypotenuse multiplied by cosine of the angle theta. So these are the two formulas that we can use to take a point which is being described in terms of r and theta and transform it into the x and y coordinate system. The formulas are that the x coordinate is equal to the distance from the origin times cosine of the angle theta, and the y is the distance from the origin times sine from the angle theta. Now these formulas are going to come up again and again and again when we talk about polar coordinates and vectors. As a quick example, let's go ahead and convert the polar point where r is 3 and theta is 5 pi over 6 to Cartesian coordinates. Now to figure out the value of x, all I have to do is take the r and multiply it by cosine of 5 pi over 6. Now this is a value that shows up on our reference circle image. And according to that reference circle image, the value of cosine of 5 pi over 6 is equal to negative root 3 over 2. Or, after just a little bit of cleaning, negative 3 root 3 over 2. This would be the exact value of the x-coordinate of this location in Cartesian coordinates. Similarly, the y-coordinate can be found by taking that distance of 3 units, multiplying it by sine of 5 pi over 6, and that would be equal to 3 times positive 1/2, or simply 3/2. This would be the exact value of the y-coordinate of this position. Now, just like there were formulas to help us to convert from polar coordinates to Cartesian coordinates, there are formulas that are based in trigonometry that we can use to convert from Cartesian to polar, to take a given x and y and produce the corresponding r and theta. Now, a similar triangle can be drawn to inspire us, one where the vertical leg is y and the horizontal leg is x, where the angle theta is drawn in the bottom right corner and the distance r is the hypotenuse. By employing Pythagorean identity, we can conclude that r squared is equal to x squared plus y squared. And to determine a formula that relates theta, x, and y, we can use the TOA part of the SOHCAHTOA formulas, which says that if you take tangent of the angle theta, then that is equal to the opposite side, in this case y, divided by the adjacent side, in this case x. Now suppose that I wanted to take the formula in green here and use it to solve for theta. Your first instinct may be to say that theta is equal to arctan of y over x. However, remember that arctan was only capable of producing angles that were between negative 90 and positive 90 degrees. So this formula, theta equals arctan of y divided by x, only works if the point xy is in quadrant number 1 or quadrant number 4, because these are the two quadrants where the angles between negative 90 and positive 90 will point into. So a different formula is needed to find theta if your point lives on the left side of the xy plane. To find the value of theta in this case, we'll use the fact that tangent repeats every 180 degrees. So tan theta equals y over x, theta equals arctan of y over x in the case that the point is in quadrant 1 or 4. Theta would be equal to arctan of y over x plus that 180 degree half rotation plus pi if your point is on the left side of the unit circle. For example, let's go ahead and convert the Cartesian point x comma y equals 2 comma 1 to polar coordinates. the very first thing that I'm going to note is that 2, 1 is the location in the first quadrant, which means that if I want to find theta, I can use the formula theta equals arctan of y equals 1 divided by x equals 2. By doing this, we get the result theta is approximately equal to 26.6 degrees according to my calculator. This is an angle that makes complete sense based on the picture where I have sketched the point 2, 1, a relatively small angle because the point is relatively close to the x-axis. We can also determine the radius. The radius satisfies the Pythagorean theorem, where r squared is equal to x squared plus 1 squared, y squared. Therefore, r squared is equal to 5. And therefore, r itself is equal to the square root of 5. I'm using the positive answer because r is a distance and distances are positive. Throughout this class, we will always assume that r is a positive number. Although some classes do find ways to make sense of negative r values, that's not really useful for us, and so we will always assume that r is positive. Now, what about the point -2, -1? Before I start to use the formulas to convert this to polar coordinates, I'm going to make a quick sketch of this point, and I'm going to note that this point is located in quadrant number 3. So it would not be correct for me to try and find theta by taking inverse tangent of -y over -x and stopping there. Because the negatives on the 1 and on the 2 will cancel out, I would once again end up calculating arctan of +½ and this would give me theta equals 26.6 degrees. And visually we can see that that angle is way too small to reach all the way over here into quadrant number 3. So that's incorrect. The correct answer to this question would be to acknowledge the fact that theta equals arctan of -1 over -2 is going to output an angle in quadrant 1. If I want to get the correct angle in quadrant number 3, I'm going to have to add a half rotation, add pi, or equivalently add 180 degrees. So this will be equal to 26.6 degrees plus 180 degrees. The true value of theta is equal to 206.6 degrees. This actually makes sense based on the drawing. To get all the way over to quadrant number 3, we would have to go 180 degrees plus a little something more. To find the value of r, meanwhile, I would take the x-coordinate, which is -2, and add to that the square of the y-coordinate, -1 squared. So r squared would be equal still to +5, and there r would still be equal to the square root of 5. Once again, only considering the positive solution because we will be sticking with the convention that r is a positive number. Now, I should add a little warning. The locations, the points, which are actually on the axes, points where either x equals 0 or y equals 0 are technically not in any of the 4 quadrants. They're sort of special locations which are directly between the quadrants. And in particular, if x is equal to 0, so that you're on the y-axis, neither of the formulas given above for theta will work. And you need to find theta manually. For example, if I was given the location where x is equal to 0 and y was equal to 3, and I sketch this on the xy plane, then that would correspond to a location which is 3 units straight up. So visually that I can see that if I wanted to get to that point, then I would have to turn through an angle of exactly pi over 2. Now if I tried to find theta not manually, but instead using one of the formulas given above, for example, what if I tried to do theta equals arctan of y over x? I'm going to run into trouble because 3 over 0 is undefined. This formula is applicable for points that are in quadrant number 1 or quadrant number 4, but it is not applicable to points which are on the axes, which are technically not in any quadrant. So if you're looking for the value of theta that corresponds to a point where the x is equal to 0, you'll need to do that manually by looking at the picture, by looking at the point in the xy plane. You cannot use this arctan formula because you will end up dividing by 0 in the formula, and that's not allowed. That concludes today's material. Today we defined the polar coordinates and we looked at how to plot a point in polar coordinates on the xy plane. Then we developed and practiced using some formulas to convert between polar coordinates and Cartesian coordinates.